Welcome to this tutorial on functional series. In this tutorial we're going to look at the concepts of pointwise and uniform convergence of a series of functions, and we'll cover several examples in order to show how to test whether or not a functional series has these properties. Previously we've looked at functional sequences, and while a sequence is not the same as a series, a lot of the important theoretical ideas do carry over from sequences to series, because we actually classify a series as convergent or divergent according to whether its sequence of partial sums is convergent or divergent. So in this tutorial, the emphasis is going to be on examples, and we're going to look at the most important tests that we need to know about and how to apply them. So to start off, here's an example of a functional sequence. We saw it before when we were looking at functional sequences. It's the sequence x over n, where we allow x to be any real number. So the sequence goes x, x over 2, x over 3, and so on. And each element of our sequence is a real valued function. Now we're looking at series of functions, which means that we have infinitely many functions added together. So suppose we have a functional series where each term is given by x over j. Then that means we actually take an infinite sum, x plus x over 2 plus x over 3, and so on, going on forever. Now just to recap, if we have a functional sequence where the terms are given by x over n, we can draw each function in the sequence on a diagram. So the first function in the sequence is the straight line f1 of x equals x, the second function is f2 of x equals x over 2, then we have f3 of x equals x over 3, and of course each function in our sequence is a straight line. The straight lines become less and less steep, and they do actually converge in a pointwise sense to the limit function f of x equals 0, which is a constant function. Now suppose we want to draw our functional series x over j on a diagram. A convenient way to do that will be to use the sequence of partial sums. So a sequence of partial sums is a sequence where each term is given by adding together finitely many of the functions in our infinite series. So the first term in the sequence is just x. To get the second term we add the first two functions together, so we have x plus x over 2. To get the third term we add x plus x over 2 plus x over 3, and so on. So if we plot the sequence of partial sums on a diagram, when n equals 1, let's say this is the straight line x with a slope equal to 1. Then the second function in our sequence is given by x plus x over 2, which is 3x over 2, so that's going to be a steeper line. When n equals 3, we have x plus x over 2 plus x over 3, which turns out to be 11x over 6, so again the line gets steeper. When n equals 4, if we add x over 4 to our cumulative total, we get 25x over 12, and you can see that this time the general trend is that each function in our sequence is actually more steep than the one before it. So from this diagram, it's not clear whether or not the sequence of partial sums will eventually converge to a limit function, and that's the question we're interested in when we investigate the convergence of a functional series. Now let's recall a well-known fact about the so-called harmonic series of numbers. That's the series that goes 1 plus a half plus a third, etc. This series is actually divergent. In other words, it fails to converge to any finite limit, even though the terms in the series are obviously converging to 0. And because the convergence or divergence of a series of numbers is equivalent to the convergence or divergence of the sequence of partial sums, we can say that this sequence of numbers is divergent. Now if we go back to our functional series x over j, we can take the x outside the summation because it has no dependence on j, and here we have the harmonic series, which is infinite. And this means our functional series tends to infinity if x is positive, it tends to minus infinity if x is negative, and obviously it's equal to 0 if x is equal to 0, because then every term in the series is 0. So given that the series only has a finite value when x equals 0, the series cannot be convergent, and our next definition will make this clear. So this is a very straightforward definition. We say that a functional series is pointwise convergent if its sequence of partial sums is pointwise convergent, and we say that it's uniformly convergent if the sequence of partial sums is uniformly convergent. So the convergence properties of functional series are based on the properties of the partial sums, just in the same way as the convergence properties of series of numbers were based on the partial sums. So based on that definition, the only way our functional series x over j can have any type of convergence is if the sequence of partial sums, which we partially drew on our diagram, is convergent. However, as we've seen, if x is not equal to 0, then the partial sum of the first n terms actually tends to something which is infinite, as n tends to infinity. And given that the domain of our functional series is R, i.e. the real numbers, it's impossible for us to define a limit function with domain R, which the sequence of partial sums will converge to. So therefore the functional series cannot be pointwise or uniformly convergent. Now it's all very well understanding what it means for a functional series to be convergent, but what we really want to know is, what are the most efficient ways of testing for convergence? And the next theorem we're going to look at is probably the most important theorem of all to know about when you're testing for convergence of a functional series. This theorem is called the Weierstrass M-test, and it works by making a comparison with a series of numbers. So the idea is that if we can show that the Chebyshev norm of each function fj in our series, in other words the supremum of the modulus of fj, is bounded above by some number aj, and we know that the series of numbers a1 plus a2 plus a3 etc. is convergent, then we can say that our functional series is actually uniformly convergent. And bear in mind that if it's uniformly convergent, that means it has to be pointwise convergent as well. So if you can use this test to show that the series is uniformly convergent, then you've actually proved both convergence properties in one go. So in order to use the Weierstrass M-test, we need to be able to show that a series of numbers is convergent. And this is where we need to remember convergence tests for series of numbers. So let's remind ourselves of some of the most well-known convergence tests for series of numbers. These tests are coming up on the next few slides, but we're not actually going to talk through any of them. So if you want to remind yourself of the details of any of these tests, you should pause the video at the relevant points. So here's the test for a geometric series, here's the comparison test, here's the ratio test, here's the root test, and here's the alternating series test. Now without any further delay, let's get on to some examples. When you're examining a functional series for pointwise or uniform convergence, essentially there are three possible outcomes that you're looking for. The series can either be divergent, it can be pointwise convergent but not uniformly convergent, or it can be pointwise and uniformly convergent. And in the second part of this tutorial, we'll have a look at some examples of each of these types.